Celsius. So you can write temperature and then degree symbol in the letter C. And on the bottom line, we're gonna do our heat energy input, and we're doing that in joules. Do you guys remember how we write joules? Capital J, you got it.
It's gonna be in degrees.
It's gonna just be heat input energy in joules. Joules aren't measured in degrees.
So heat and then the apostrophe J.
Yeah, you could do heat and then in parentheses do a capital J. But it's heat input, so make sure you put your input in there. That way, you know that you're adding that temperature difference. Or I'm sorry, the heat input difference, excuse me. Is everybody labeled? Give me a thumbs up if you're done. All right, we'll give it another minute.
All we needed was the phase change diagram, the temperature, and then the heat input.
That's correct.
Okay.
Yes, ma'am. And then we're gonna mark where our 0 degrees is and our 100 degrees is just to get started. Let me see what, if you guys has, okay, you see how there's like a little bit of a thicker line and then they're almost like in grids, like, do you see the thicker lines?
Yes.
Okay, so on the second one up, you guys are gonna draw a line straight all the way across horizontally. And if you guys have any colored pens or pencils, using a blue would be great. Do we have any blue or colored
Is there any
pencils?
way that we can get that on the board?
Do you have, or do we have one of these on the
It's
board?
gonna play up there.
Oh, okay, we're just setting it up right now, and then we're gonna watch the video, and the video is gonna guide us through creating this diagram.
If we'll do that first diagonal.
Okay, yeah, I was gonna have them do the 0 degrees and the 100 degrees, and then, okay. So draw your line across. If you have a blue, great. If it's in black and white, that's perfectly fine. Just draw a line thick enough that you can see it to know that that is our 0 degrees Celsius line.
The second.
In the second one up here. So if you look here on the bottom of it, there's a kind of a thicker line that runs, and on the second one up, you're gonna draw a straight line across. And then you're gonna label it over here on the left at 0 degrees. And we've already labeled this Celsius, so you just have to do 0 degrees. You don't have to list it individually.
And we'll let this play.
What do you want? Let me do the 100, that way when they draw the line, it's there.
It'll take us.
It'll
through.
do it? Okay. All right, guys, now we're gonna watch this video and fill in our chart. Is everybody good to go where we are right now? Everybody has their title, their temperature, heat energy input in joules, and their 0 degree line. Give me a thumbs up if you have all of that. Ladies, do you have yours all set up? Not yet? Okay.
I have just the line written out.
That's fine. That's, yeah. If you have
What's
the
a
line, you're
phase
okay.
change diagram, you ask? And why is it important? Why do I need to learn about it? Well, a phase change diagram is a very useful and kind of universal tool that scientists can use to tell a story about what happens to a substance as heat energy was added to it and its temperature changed. It's a very common tool in a physics or chemistry class, so you should become familiar with it so that you can solve problems more easily. In this case, I'm going to make a phase change diagram that tells a story about an ice cube that receives some energy from its environment.
Oh, my bad, guys.
Maybe it starts out at a negative temperature, like negative 50 degrees Celsius, and we've heated it up until it reaches 0 degrees Celsius.
All right, so we have our negative degrees Celsius, which we're gonna start down here in the bottom left corner, and we're gonna heat it up to 0 degrees. So you're gonna draw your thick line from your bottom left corner up to that 0 degrees Celsius line that we drew when we started. Yes, ma'am.
A question for the 100 line.
Yes, ma'am.
Is it the same like the 0 line we have at the bottom, but it's just at the top?
It is, but we're gonna get to it because it's gonna come up in the video where we need to draw that line. I just wanted you to do the 0 line, that way when we started, we were already set up.
Can I go ahead and draw
If you wanna go ahead and draw it, that's fine, because we're gonna get to it.
Can I do it in blue?
You can do it in blue if you'd like, but if you have a red, that would be better. That way you know that that's gonna be our hot and our cold is blue. Just to visually, when you guys look at it, you can remember that it's hotter up higher, you know, higher temperature. Just a visual cue. So I want you guys to all have this line drawn from here, the bottom left corner, up to your 0 degrees Celsius. And see, it's only 3 grid squares in, so don't draw it all the way across, just follow the same pattern. Does everybody have this line drawn?
Oh, no, not yet.
No? Okay.
Do you want it in black?
Yes, black would be fine.
You're fine.
Where should I put
Yep, that looks
Just
good.
start at the origin and go up.
Yes, perfect. So this is your, yeah, your origin is gonna be the very center of your graph here, where your X and Y meet.
As long as we have some idea, this is a conceptual idea that we're not gonna put numbers on it, so we'll be okay.
Let me get a thumbs up when you guys have this line drawn, please. Okay.
C6 watching this.
I'll try to stay in here.
I'm like, okay. You can move. You ready for this?
Oh, I'll do it. I'll pause it.
Okay.
All right, give me a thumbs up if we have that line drawn. Perfect. All right, guys.
And what happens afterward? Well, what just happened now is that the solid was heating up.
All right, so label that on your guys' graph. So what did we do? We were at negative degrees, and we increased the 0, so our solid was heating up. So we're still in a solid state, but it's starting to get warmer so that it can start to get into a liquid state. But right now, we're still solid. Great job. Looks like everybody's about got that. Thank you for the thumbs up. Everybody good to go? Good to go.
Celsius, and we've heated it up until it reaches 0 degrees Celsius. And what happens afterward? Well, what just happened now is that the solid was heating up. Makes sense, because we added heat energy to it, so its temperature increased. What will happen next if we continue to add heat energy? Will it go from 0 degrees Celsius to 10, to 20, all the way up to 100 and beyond? Well, actually, no. You might be surprised to learn that if we continue to add more heat energy after this point, we will actually not see a temperature increase. Instead, our graph will plateau, which means to go flat for a while. So we'll keep adding heat energy, and we'll keep...
Why do you guys think it goes to a plateau? Why does it not just go straight all the way up from negative degrees all the way up straight to 100? So this here, so every line that we draw is going to be a different phase. So this doesn't just go from a solid straight up to a gas. It's going to step up in levels. So why do you think that it doesn't just continuously go? Why does it plateau? So I have a solid ice cube, and it's solid, right? And we're adding heat to it. So if we're at a solid and nothing's moving, we're all the way together, and when we add heat, right, so all of them have to come together. All of them have to move enough at the same time to come apart to become a liquid. So ice doesn't melt instantly. When you put an ice cube on your counter or when you drop one on the floor and kick it under the fridge, it doesn't just melt all of a sudden. It slowly melts. And that's this phase change that we're going to talk about right here. The plateau line is while it's waiting for all of the solid pieces to break apart, for those molecules to start moving around again and become more of a liquid state. So this is waiting for all of the molecules to collectively come to the same state of matter.
Keep adding heat energy, and we'll keep adding heat energy, and yet there will be no increase in temperature for a little while. Scientists, I assume, were baffled when they first started tracking these things and noticed that adding more energy did not increase the temperature of things like ice. And what they eventually realized is that there was some extra kind of energy that you needed to add in order to make a phase change occur. So that's actually what's happening, is the particles inside of the block of ice are changing from solid into liquid.
Okay, so they're, like I said, they're changing from a solid to a liquid state, and it doesn't happen instantly. The ice cube doesn't hit the floor and instantly melt. So on our plateau line that we're drawing across, and remember, just keep it short because we have to take this graph all the way across, we're going to label that that's our solid melting. So it's just a time lapse that's going to take that solid to melt. So
If we would also, under melting, if we would put MP, that's our melting point.
oh, perfect. Yes, thank you.
Where do we put melting point?
Right after your solid here.
That is where it says put MP, that's our melting point.
Gentlemen, have we labeled? Yes, thank you. Everybody good to go? All right, good job.
So this is the part of the graph that shows the solid melting. Now, at the beginning of this plateau, all of the block of ice is solid, but by the end of this line, all of the block of ice has converted into a puddle of water. So now it's all liquid. So on the left is all solid, on the right is all liquid. But you'll notice it's the same temperature throughout that whole process. The heat energy in part 1 of this graph caused the temperature of the individual molecules to increase. They were vibrating more, so they had a
Please sit
higher
down, sir.
temperature. But the heat energy in part 2 of this graph was doing a different job. It was taking the molecules and breaking apart the bonds between them so that as a liquid, the molecules can slide past each other more easily. So, what happens once all of the molecules are liquid? Well, at that point, you have
Why don't you guys tell me what happens when all the molecules are liquid and we're still applying heat?
Boiling.
Boiling, does it instantly start boiling? It goes from liquid to boil?
It just starts getting warmer and warmer.
Do you think that takes a long time or do you think that's fast?
Pretty fast.
Long time, fast time? I guess it's all relative to what you think long and fast is. If you put a pot on the stove to boil, does it boil right away or does it take quite a while?
It takes like 15 minutes.
Yeah, if you stare at it, it'll take longer. All right, guys. You guys are on the right
A
track.
watch pot never boils.
0 degree liquid water. So then if you add more heat energy at that point, going farther on the x-axis, then the liquid can start to heat up again.
All right, so what are we going to write on our increasing line here?
Liquid heating up.
Liquid heating up.
Is that good?
And if you guys haven't already done so, you guys can draw your 100 degrees Celsius line like I have here on this graph. It's that second thick line down is where this one is drawn across. If you have a red color, that would be great. If not, that's perfectly fine. And we have another change and we have another plateau and another change coming up. So make sure you leave room on the right side to draw your additional lines.
Beautiful.
Perfect. Looks like you guys are about there. All right, let's keep moving.
Like before. So we get this next part of the graph that's going up like this until we reach 100 degrees Celsius. What's going to happen at that point? Well, you can probably guess that something similar to before is going to occur. Before the temperature of this water can rise above 100, it first needs to be boiled and converted into steam or gas or a vapor.
So steam, gas, or a vapor. So we're gonna heat up our liquid, and then we're gonna plateau again, and that's our liquid boiling, and that's our boiling point. So in addition to writing liquid boiling, you're gonna put a BP on it for boiling point.
Oh my gosh. So professional with it.
You guys look great. You guys are doing a fantastic job.
Oh, from down there to up, and then you just do another line over like that.
Yes, you'll have your plateau on the top.
It's also on the blue.
Yeah, I know, but
Trying to keep them out of it too.
Yes, sir.
Yeah, better keep me out of it.
Ma'am.
So if we drew this line here, at what temperature is our boiling point?
100
100 what?
degrees or Celsius.
Yes, 100 degrees Celsius, you're correct. Why is it in Celsius and not in
I
Fahrenheit?
almost said Fahrenheit. That's why I repeated Celsius so many times.
Okay, why is it Celsius and not Fahrenheit? What do you got, Austin?
because we're measuring water, and Celsius is based on water because the 0 for Celsius is when water freezes.
Yeah, 0 degrees Celsius is when water freezes and 100 degrees Celsius is when it boils. But we use Celsius because in the scientific community, we always communicate in the same forms. That way, if we do it here in America, if we give that information somewhere in Europe, or if it goes to Japan or China, everybody wants to use the same system and everybody uses Celsius except for us because America is special like that. Instead, we look at our feet and measure things, which is weird.
Huh?
Okay. Well, I was just saying because we don't use the metric system. All right, is everybody caught up and everybody's where we are? Okay, great job.
And that takes extra energy, just like melting took extra energy. So at the beginning of this new plateau, we have 100-degree liquid water, and by the end of this plateau, we have 100-degree steam, all in gas form. And this flat section of the graph here shows the transition between those two states, between all liquid and all gas. Once all of the liquid water has become all gas, then the temperature can exceed 100 degrees and go higher than the boiling point, and at that point the gas can heat up. And this is where we're ending the graph because it's not very interesting after this.
Okay, so we were at our boiling point for a pretty significant amount of time while we're waiting for all of it to heat up and all of it to boil. Just like when it was ice and it was all solid and we had to wait till it slowly loosened up into a liquid. And now we're gonna go all the way out and make it into a gas form. So they're all gonna be, all of your atoms are gonna be spread apart into a gas form. And make sure we label it gas heating up here. It looks great, good job.
Beautiful chart.
It's beautiful, I like to use colors, that was a good job.
Pink and blue.
Before. Keep
And if we have a little bit more room, I should have mentioned at the beginning, I'm sorry. We're gonna add a little bit of information here on the very top line. So if you've already gone to the top over here, that's okay. We're just gonna squeeze it in over here. And it's just gonna be images so that we remember what a solid looks like, how close the atoms are. And if we move into a liquid solid state, then the molecules are gonna be a little bit further apart from each other until we get to a liquid where they're pretty far apart.
And that'll be on the video also.
This is the end of the video, right?
It'll continue playing.
Oh, it does go, okay.
Gas can just keep getting hotter and hotter and hotter until it eventually becomes a plasma and the molecules rip themselves to pieces, at which point this type of graph becomes meaningless. So we'll just stick with solid, liquid, and gas for now. Now remember that this was called a phase change diagram. Well, the diagram part means it's something visual, it's a graph, and phase change means it's pointing out that a phase change of melting and the phase change of boiling requires some amount of extra energy.
Okay, who wants to recap what he says in your own words? Did everybody understand what he was saying? Like, what is the phase change? What do you have to add to create a phase change?
You need extra energy.
Yes, you got it. You need extra energy to create a phase change. Good job.
So what's the deal with the extra energy we had to put in? Well, that's referred to as latent heat.
Okay, so the extra energy we put in, what was it called? Latent heat. Oh, we don't have it recorded on this, but that's just for you to know. You don't have to, well, if you want to write it on your chart, somewhere over here, the latent heat, and maybe point that to where you're adding it, which are your plateau lines, because that's that latent heat that's just getting pumped in, pumped in, pumped in, while it's making those molecules go further and further apart. So that's the specific type of heat is latent heat. So if you want to draw it and point an arrow here, point an arrow here, somehow signify it so when you look at it again, you can remember that that plateau line is applied latent heat. Give me a thumbs up when you guys have that done. Gotcha. 3. Cool, good, okay. It's L-A-T-E-N-T. I know it might be hard, and then heat, H-E-A-T.
I just pointed at a plateau line.
Point, yeah, if you point it at a plateau, that's perfect. Let me get a thumbs up if you haven't already given me one. Great job. All right.
Latent is an old-timey word that means hidden or secret or unseen.
Oh, cool. I
So we-
was unaware of that. So unseen or secret heat. It's kind of a fun fact to know.
Call it latent heat because scientists didn't originally know what this extra energy was doing. Extra latent heat, it turns out, must be added in order to change from one phase to another. So you need to put extra latent heat into a solid to turn it into a liquid, and you also need to put in extra latent heat to turn a liquid into a gas. Finally, the most important thing you can learn from this phase change diagram is visually you can see that during a phase change, temperature does not increase. When the solid was
Okay. So during the phase change, temperature does not increase. We don't need to write that, but we need to know that. So why does it not change the temperature? Why is it steady heat or steady temperature? If we're adding heat to it, how come it isn't changing the temperature? What do you have, sir?
The energy is changing from one phase to another until they all change. That's why we have the plateau.
There you go. So we have to wait for all of the molecules, just like when we were over here and we had our solid, we had to wait for all of the molecules to go from a solid to breaking apart to becoming a liquid. So while that's happening, no heat is increasing, instead the molecules are just being pulled further apart.
And this is where I make them do the solid, liquid, gas, and then they have to do a Hercules. That's their cheer.
We don't do that. He's
Okay, so in latent heat, does temperature change?
Yeah.
No, it does not. Good job, guys.
It's melting, it started at 0 degrees as solid and ended as still 0 degrees, but liquid. And same thing up above. We talked about how this part of the plateau is 100-degree liquid, and this other end is 100-degree gas. So temperature does not change when you're doing a phase change. It's either one or the other. You're either increasing in temperature or you're changing phase. So keep that in mind as we go forward and look at more phase change diagrams. Here's one that helpfully shows up at the top a visual of what's going on in the molecules during these 5 parts of the graph.
Okay, so this is what the molecules are looking like. So on the very top of your graph, if you have taken it to the top, just fit it in the best you can. And you're gonna like do an invisible line here. So just like these are actually. So draw, a tacked line or a solid line, whatever you need to do, so that you can look at it and know that this section here, as a solid, all of your molecules are packed in together, like an ice cube. They're all just packed in super tight together. And then when it goes to that liquid stage, they're somewhat together still because this is the latent heat phase, so they're still doing a phase change in this section. So it's not quite a liquid, so you can still see here there's a cluster that are still frozen together. Those molecules are still tightly bound. There hasn't been enough latent heat applied for them to start to break apart. Are you confused? Am I gonna help you?
No, I'm not confused. Do I need to put it down if I already knew all of this?
Yes, put it down. That way when you go to take your test or your exam, if you maybe get anxiety or forget about it, just label it down. And the best way to learn something is to go teach somebody it. So if you guys are confused about this, I want you guys to teach somebody about it. Maybe at the end of the class, you guys can ask each other questions. Yes, so you're gonna also do your liquid solid, and then over here your liquid, they're just kind of spaced apart. And then when you get to a liquid gas, notice that you still have liquid molecules down here on the bottom that are not floating because it's still, like I said, in that latent heat phase. And then by the time it's a gas, they're all pretty far apart. So label all these sections of your diagram, please.
When they're finished, they can just turn it into the folder over there and I'll get it correct.
Perfect. Is this clock correct?
Yeah, they've got 12 minutes.
Okay, great, yeah, no problem, guys.
14, 15, 16. They got about 17 minutes left.
Okay, great. Yeah.
We have 23 minutes, we're good.
Oh yeah, I needed 15, so that's perfect, thank you.
So, is there anything else you want to say at the end?
Give me an A. No. That's
Is
fine.
that for your class?
Yeah, it's for a class. Oh, okay.